So I will be discussing capacitor types. There are three types of capacitors in this course, and they are the spherical, cylindrical, and what's called a parallel plate capacitor. The parallel plate capacitor will be the most important, but the spherical and cylindrical capacitors are excellent applications of Gauss's law and a good review for the test to come. So first, let's define what capacitance is. Capacitance, defined as C, is charge that you put on one of the plates of the capacitor divided by the change in voltage. And just to remove any ambiguity, because the change in voltage can either be positive or negative, we'll put an absolute value sign around the change in voltage. So that's the way capacitance is defined. Charge is measured in coulombs and voltage is measured in volts. So capacitance C is basically coulombs divided by volts. The special unit given for capacitance is farads, after Michael Faraday, the great scientist. So farads are the units of capacitance. Now, if we were to find the capacitance of a spherical capacitor, which consists of two plates, the inner plate of radius A and the outer plate of radius B, we would first have to find the change in voltage between the two plates. And whatever charge I put on the inner plate, the opposite charge should be on the outer plate. The net charge of a capacitor is always zero. So let me first proceed by taking some Gaussian surface. Yes, those Gaussian surfaces are back to haunt you. You thought you were done with them, but no. This is a fixture of the course. So let's take some Gaussian surface of radius r, which is the generic radius of a Gaussian surface, and find out how much electric field there is at every point on the Gaussian surface. Now, this has got spherical symmetry, so we can certainly write down Gauss's law using spherical symmetry. The left-hand side of Gauss's law will be E times 4 pi r squared, following the spherical symmetry arguments, and the right-hand side is just the enclosed charge, which in this case is Q, divided by epsilon naught. And so we get the electric field of this spherical capacitor's interior between the inner plate and the outer plate is going to be Q divided by 4 pi epsilon r squared, just as it would be for a point charge. Now the change in voltage is the change in voltage between the inner plate and the outer plate. So the best way to find that out using the master equation is to integrate it from some path that goes from r equal to a to r equal to b. I'll draw that path like that. So let's perform the integration. The change in voltage, delta V, which is going to be V of b minus V of a, because the final is at b and initial is at a. And that's going to be minus the integral from a to b of this electric field. It's pointing outward because it's a positively charged inner sphere, so electric field is pointing outwards, and dr vector is also pointing outwards, so it's going to be E times dr times cosine of 0 degrees. Now Q and 4 pi epsilon naught are all constants, so I'll pull it outside the integral sign. So this gives me delta V equals negative Q over 4 pi epsilon naught, and the integral of 1 over r squared is negative 1 over r. So I'll remove that negative sign by making this positive. So I get 1 over r between the limits a and b. So we're almost there. And that's going to be Q over 4 pi epsilon naught. Put the limits in, 1 over b minus 1 over a. Now you'll notice that 1 over b is going to be a smaller quantity than 1 over a because b is bigger than a. So this is going to be less than 0, which makes sense because the change in potential has to be less than 0 if the electric field is pointing in this direction. The electric field will be pointing in the direction of the green arrow because electric field always points from positive charge to negative charge, or said another way, electric field always points from a region of higher potential to a region of lower potential. So delta V is less than 0, which means it's a good thing we have this absolute value sign. Let's find out now the capacitance of this object. The capacitance of a spherical capacitor, which I'll write as C SPH, is equal to the charge Q divided by the change in voltage, which is all this stuff. So that's Q over 4 pi epsilon naught 1 over B minus 1 over A. I'm going to write that as A minus B divided by AB by taking the common denominator. And I have an absolute value sign. The Q's cancel out, and so I get this as 4 pi epsilon naught, because this is in the denominator of the denominator, so it goes to the numerator, times AB divided by B minus A. You observe that I have interchanged B and A to make this quantity guaranteed to be positive. One thing I want to point out right away is that one of the important features of a capacitance is that a capacitance looks like epsilon naught times length. It's proportional to epsilon naught times some length. Basically, if you hit epsilon naught with some length, you will get a capacitance. And that's a very useful principle, which means that any object that's got a length has got a capacitance. So does this pen have a capacitance? Sure, it does, because it's got a length. It's as crazy as that. And because of that, because of this principle, the capacitance is proportional to epsilon naught times length, some length factor, because AB is length squared and B minus A is length. Epsilon naught itself gets new and snazzy units. Because capacitance is measured in farads, farads equals units of epsilon naught times meters. So the units of epsilon naught are in fact going to be farads per meter. Not that crazy unit that you are used to using it. The units that we have so far is 1 over the units of Coulomb constant K, and the Coulomb constant K has got unwieldy units, but this is how people speak. Now if you look at the value of epsilon naught is 8.85 times 10 to the minus 12 farads per meter, or said another way, it's about 9 picofarads per meter. 1 meter of anything has got 9 picofarads. All right, now let's go to cylindrical capacitors. Now here you have to cheat a little bit. Remember, all the Gauss law stuff is not true for finite cylinders. It's only true for infinite cylinders, but we're going to play a game where we'll say, oh, well, it is looking pretty infinite right now, so I'm going to apply Gauss's law, and then once we have our results, we'll kick Gauss out and work with a finite object. So that's the trickery we're going to play. So using Gauss's law, the left-hand side is going to have E times 2 pi r L for cylindrical symmetry, and that's going to be the total charge over epsilon naught. Well, now we're going to play the trick. We're going to say the total charge is Q. Haha. Because previously you could not have said that. The total charge could not possibly be finite for an infinite cylinder. But now we're going to turn things around and say, sorry Gauss, it is Q. So the electric field, E, is going to be Q divided by 2 pi epsilon naught L times R. Okay. Now we have to find the change in potential. We'll play the same game, take the radially outward path. So change in potential, delta V. No purpose was served writing it as V of B minus V of A, so I won't write that now anymore. It's minus integral A to B, E times dr cosine 0, because we're going to take the radially outward path just as we did for this one. We're going to take the same radially outward path for that one too. I'll indicate that path here. Now let's compute. This is just going to be, all the objects here are constants, so I'll bring them out. Q over 2 pi epsilon naught L integral from A to B dr over R. Well, that's just a natural log, so that gives me negative Q over 2 pi epsilon naught L natural log of B over A. It's ln B minus ln A, which I can write as ln B over A. Finally, the capacitance is, by definition, capacitance is charge over change in voltage. And here we have to get rid of this minus sign. since B is bigger than A, natural log of something bigger than 1 is always positive. So that's no worry there, but we still have a negative sign here. So the absolute value signs will take care of that. So I have Q divided by 2 pi epsilon, Q divided by 2 pi epsilon naught L with that minus sign, natural log of B over A. All right. So now we can do the same thing, cancel out Q's. The Q cancellation always happens. Capacitance does not depend on how much charge you have, in the same way as the capacity of a water bottle does not depend on how much water there is. So there's going to be 2 pi epsilon naught L divided by natural log of B over A. Now notice it has the same feature, that capacitance is epsilon naught hit with some length, because natural log of B over A has no units. There's another feature I want to point out that's really crucial here, and that is as B goes to A, you notice that if B comes close to A, if the two plates approach, then ln B over A is going to be 1. Natural log of 1 is 0. The capacitance is going to go to infinity. It has the same feature over here. If B goes to A here, the denominator is going to become 0 and the capacitance is going to go to infinity. So that's another property. As plates approach, the capacitance goes to infinity. So one way it might seem to make a big capacitance capacitor and store a lot of energy is to really bring the plates very close. But there's a big problem with that. If you bring the plates very close, they'll of course try to attract, because opposites attract. Now let's go to the last thing here, which is the parallel plate capacitor. Now this by far is the most important capacitor, and most capacitors that you find in applications in electronics are actually parallel plate capacitors, even though they look like cylindrical capacitors. If you open any amplifier, it'll have a big capacitor that looks like this, but it's actually a parallel plate capacitor that's been wrapped up many times to fit into a smaller volume. So how does this work here? We're going to assume that there's a charge plus Q on this side and minus Q on that side, and we're going to play the same trickery with poor Mr. Gauss. We're going to use the electric field of a conductor. Now let's play this carefully. The electric field is going to be given by this Gaussian surface. So there's going to be some field coming out from this surface, but nothing coming from this surface, because it's inside the metal. So there's going to be field coming out of this surface. Out of this surface, it'll be perpendicular to the area vector, so there will be no contribution. This inside the metal, so there'll be no field there. So when you do E times A, I will get sigma times the area upon epsilon naught. That is the way we do this. So electric field in between the plates is just sigma over epsilon naught. Now once you have that, let's find the voltage difference. For the voltage difference, you will go from here all the way to there along this path, and since this is a one dimension, I'll just call this the x direction, x hat. I'll call this x equals 0, and that plate location is at x equals capital D. Capital D is a notation for the distance between the two plates of a parallel plate capacitor. So the change in voltage, delta V, equals minus the integral from 0 to D of E times dx times cosine of 0 degrees, because the electric field is going to be pointing from left to right in that direction. Okay, that's the direction of the electric field. Let's calculate this. That's going to be negative sigma over epsilon naught times d, because the integral of dx is just d. Now let's put what sigma is. Sigma is the charge q divided by the plate's area. So again, poor Mr. Gauss said that you can only use this if the plates are infinite. We say, no, we're going to do it anyway. So finally, the capacitance of a parallel plate capacitor is going to be the charge Q divided by the absolute value of the voltage. That absolute value of the voltage will take care of this minus sign I get here. And so Q's cancel out once more, and I have this really famous formula, epsilon naught A over D. And so just to emphasize that this is the only formula I really care about in this particular course, I'm going to only box this one and not the rest. Only this gets the honor of a box. All right. Let's see if the three properties of a capacitor is satisfied. It looks like epsilon naught hit with some length. Yep, because area is meters squared, D is meters. It does look like that. If the plates approach, the capacitance goes to infinity. Sure, it does. If D goes to 0, capacitance goes to infinity.